Okay, so today I'm going to provide you one more examples for the method of transformation. Okay, so I'm not going to repeat again for the definition, which is what we have provided in the past two lectures. And today I'm going to focusing on a particular task by introducing a T distribution with degree of freedom K. And I'm going to use the method transformation to introduce you this new distribution. So the concept or the new distribution is not of a concern. It's more of the method that that we go over in the past 2 weeks, that will be showing up in the final exams. So it's the method or the procedure that matters in terms of the exam. Okay. But throughout this process, I'm going to introduce you a new distribution called T distribution, which is I'm pretty sure you all use it. It's just you didn't recognize that you are using the T distribution. Okay. Last time we also mentioned that when Z1 to ZK, if they follow IID standard normal, that means with mean 0 and variance equal to 1, then if we perform particular transformation, let's denote it as V, which is the summation for all these K copies, and then for each of the ZI, when you're taking the square. So for each of the IID standard normal variables, you take a square and then sum them together. This is called a chi-square degree distribution with degree of freedom K. Okay. So last time we provide the moment generating function of the variable. So if you look up your lecture notes from from Tuesday, you will have the moment generating function of this new random variable, or this chi-square random variable, is equal to 1 minus 2t raised to the power of negative k over 2. Okay, so we use the moment generating function to show that this is the moment generating function for the random variable v, which is just the chi-square random variable. And we're recognizing that this shares the same moment generating function as the gamma distribution. So essentially, the chi-square random variable is a special case of a gamma distribution as well. Okay, so V is also following a gamma distribution with parameter the alpha equal to k over 2 and the beta equal to 2. Okay. So we call V follow is a chi-square random variable or follow a chi-square distribution, but V itself is also a special case of a gamma distribution. Similarly, when we work with the exponential distribution, we write a random variable following an exponential distribution, but exponential distribution itself is also a special case of a gamma. So there are lots of variables that are just special case of each other, and then you can also come up with your own distribution or random variables, and then from there you can calculate the probability of interest of some events. Okay. So again, the core of all the probability is centered around the probability density function. And then through lots of the manipulations or techniques that we introduced throughout the lecture, you can play around these density functions and then calculating the probability of the events of interest. Okay, so this is what we have from Tuesday. Any question up to this point? Okay, now here in this picture so far, we have two random variables. One is called the standard normal and the other is called a chi-square. Now let's introduce one more transformation. So let's denote this capital letter T with the following transformation, where we have a standard normal on the top and then a chi-square random variable divided by its own degree of freedom, taking the square root. Okay. So here, I'm introducing a new transformation where z following a standard normal, and then v following the chi-square distribution that we just introduced. Okay. And this is a new transformation, and I'm going to denote this by a capital letter T. So our goal in the end of the lecture is to find out what is the marginal distribution of T. Okay. But in order to obtain this probability density function, we will need to use the method of transformation to get the joint, and then I'm going to show you another trick to marginalize the other random variables to get a marginal here. So again, the marginal is coming from, so if you still recall the lecture from 2 weeks ago, we will have the conditional multiplied by the marginal. Okay? So this is the joint, and then we have the conditional and the marginal. So the method of transformation is working on the joint distribution. But here, in the end, we are going to obtain this particular marginal distribution for the T random variables. Okay, so that will be our goal here. So more explicitly, we want the formula for the density function for the new transformation T. Okay, so now we have let me just provide a quick summary of the information that we have here. We have z that following a standard normal. We have a v that following a chi-square degree of freedom k. We are interested in a transformation that call z over the chi-square random variable divided by its own degree of freedoms. Okay? And I'm also saying that we are going to use the method of transformation to get the marginal density function for this T. So first of all, we are going to obtain a joint distribution. So that means we need another transformation. And then for simplicity, we can just introduce another transformation S and then let it equal to V. And the strategy is that we are first going to find the distribution of the joint, T and the S, through the method of transformation. And then to get the marginal density for the T only, there's another trick. You can just integrate this joint distribution with respect to the random variable that you are not interested in. So here, when we integrate all the possible value for the S, then you can obtain the marginal only with respect to the T as the marginal. Okay. So here you will obtain the marginal distribution. Okay, but in order to perform the second steps, we need to use the method of transformation to get the joint in terms of the T and the S. Okay, what we have is only the standard normal and the chi-square random variable. What we need is first a joint distribution for the new transformed random variables, and then we take the marginalization to obtain a marginal distribution. Okay, so that will be our strategy here. So this is step 1, this is step 2. Okay. Yes?
What's the point of letting S
Just for simplicity, and then it will be easier to performing the integrations later. Hmm? Because you need two more new transformation in the. Okay, let me show. So, to use the method of transformation, you need to have your original random variable. So this is the z and the v here. You need two more transformations. So this is the v. This is the other one, the t and the s. So you need to using this procedure to find out the distribution for t and the s. So you need two new random variables, and then their connection is through these transformation. So this is the v over the z over v divided by t, and then you also need another transformation. But for simplicity, the integration that we will perform later, setting v equal to s, is very simple for the downstream computation. Yeah. Okay. Again, I'm just showing you all the like the procedure of using this formula again and again. So last time we have the one example for the gamma and beta distribution, and also we have today we're going to use this to introduce the t distribution. So the final result I'm not going to test you, but I just keep showing you again and again how to use this formula to derive new results. Okay, so it's more like a procedure instead of the although the final result is also providing you lots of statistical insights. Okay. But again, the point is that I'm showing you how to use this transformation to get something. Okay. Any question, comments? Yes.
Just to clarify, because I don't recall this, f of then subtext y1, y2, then parentheses y1, y2 is saying a function with respect to y1, y2 with inputs y1, y2. What does that exactly mean?
Which part are you referring to? The G's or the H?
The second line. I don't really understand what that means.
The second one?
The second line from the top.
This one?
Yes.
Oh, okay. So, again, let me see if I can. Okay, so let me use the example in the practice midterm 2 again. So, do I have? Okay, so what you have is that okay, so in practice midterm 2, you have seen something like you have 2 points, A and B, and then you have 2 different routes to travel from A to B. We know that X and Y are the minutes that you can spend. But this is a random event. You could spend 30 minutes on Monday, you can spend 31 minutes on Tuesday. So it is a random variable. So different times or different days you could have different actual number. But so it's a random event. So you can use distribution to model to measure that. Okay. So now let's say in the exam I was asking you a transformation. So you can also call this as a transformation. The differences between the 2 routes. So when you're taking a difference, and I'm also asking you to calculate the probability of the difference, right? And then you find out it's about like a 0.5. So this is a transformation of the given information. So the information that you have is the individual minutes that you need to use by traveling the routes. But sometimes the business or in your analysis, you're more interested in some transformation of the quantity that you provide. So I might provide you lots of patient data, patient 1, patient 2, patient 3. But what you're interested is a transformation of all the patient information that you have. So let's say X bar is the sum of the patient's vitals and then each of the Xi following some normal distribution. This is the information you're provided. But the things in your analysis is that you're interested in some transformation of that. So that's why we are working on transformation instead of the information that you're provided. Yeah. So here, let's say if you are provided like 100 patients' vitals, But what you're interested in is not an individual patient. You're interested on the average or even some transformations of that. Maybe 1/3 x bar, and then you think that transformation is will provide some insight on your analysis. Then you're working on a transformation of the information that you are provided.
So syntax is just saying, considering these two
New
inputs.
yeah.
Oh, then they are in themselves transformations, and then what's in the parentheses are the two random variables.
Yes.
Okay, thank you.
Yeah. Any other question or comments? Yes.
So in the problem that we were doing, T and S are the transformations?
Yes. So T and S, the form, are the G's. Okay. Yeah. So here, if you are referring to the notation in the definitions for the formula, then these are the G's. So these are function of G that input Z and the V. Yeah. Any other question or comments? Yes.
Why does integrating the transformation, the combined transformation by one transformation, remove it? Exactly. I wasn't under the impression that it's an integral of other transformations. Like a transformation of two separate transformations is in itself like a derivative, or so like how I don't understand why mathematically an integral with respect to a transformation removes the transformation entirely.
So the key idea here is that you are aggregating all the possible value of S.
Sorry, very quickly, it's covered up on the screen.
Which one?
It's covered up on the screen.
Yeah. So here you are taking the integral for all the possible value of S. Once you consider all the possible value of S, then you essentially just removing that that random variable away from the picture, and then you will have all the marginal of that. So let me see if I can provide a picture for that. So kind of like when you have a joint distribution, you will have a contour for X and Y. Now you are considering all the X here, then you kind of essentially squishing all the X into the Y axis, then you will only have the marginal of the Y for all the possible value of Y, something like that. So this is a 2D case. When you have two random variables, you will have a contour. But when you're squishing all the possible value of the S, or here is the X, into one dimension, then you basically remove that, or squishing all the information on one dimension, then you will have a marginal of that for one variable Y. You're removing the X away from the picture.
Okay, thank you.
But that is a visualization for that. But in mathematical language, you need to take the integral of the things that you don't want. So you don't want X, and then you squish them, and you will have the Y over. You have the density for that Y. Any other question or comments? Okay. So to implement the transformations, and also using the notation from the formula, again, T is a function of the V, Z, and the V. And by definition, or by construction, we let this be z over the chi-square random variable divided by scalar k in that. So that is your G1. We also for simplicity, we also define S, a function G2, also a function with z and v. Your original random variable is equal to v. Okay, and if you want to include the z, you can always add it 0 multiplied by z. So this is kind of like a function that, again, inputting two variables, but you can add a 0. So that is still a function of two variables. So these are the G1 and G2. To use the method of transformation, we also need the function h1 and h2, the inverse of this. You input the t and the z, you input the t and the s, and then you obtain the original random variable back. The original here is the z and the v. Okay? So here, to obtain the inverse function, the z is equal to t multiply by v divided by k, square root of that. Okay, so I'm just starting from this transformation by moving the z on the left-hand side and then everything else on the right-hand side. However, this is still not yet a function involving the new random variable because we still have the v. But now we can replace the v by s. This is your h1 inverse, a function that you input t and the s, and then output the original random variable z. Okay. So again, your transformation is a transformation using the old or original random variable z and the v. So you can see that you input z and v, you obtain the new one. You input z and v, you obtain the s. To use the method of transformation, you need to use the inverse function. The inverse function is a function that input the new variables but obtain the original random variable back. So that's why I call inverse. Okay? And this formulation is the formulation for the h1. That you input t and s, you obtain the z back. Okay. Now we also need the inverse function for the v. And because we define s equal to v, so the inverse function for v is just v equal to s. Okay. And also, if you want, you can always put in a 0 multiply by by t. This is your inverse function. Any question up to this point? Yes.
So why did we pivot from having s equals v plus 0 times z to v equals s plus 0 times v? I get that they mean the same thing.
Oh yes, this is just for pointing out that this is a function of two variables. You can also remove it. If you don't want, you can also just using that. Yeah, I'm just making it, emphasizing on that this is a function of two input, but you can always using a 0 multiplied by the other input to silencing that input. Yeah. But I still want to keep it here, just for clarity. You can always input as many input if you want in a function, and then you can use a 0 multiplied by that to silence it, to removing that. Okay. So now you have the transform random variables that you are interested in. And then here we also have the inverse function, that the component needed for using the method transformation. Any question or comments up to this point? Okay, next we are ready to calculate the joint for the t and the s. What are some component, or one more component that we need to calculate here? The Jacobian, right? And then my follow-up question would be whether we should use J1 or J2 based on the information. Based on these four formulas here, how do you choose? Or although it's up to your preference, but what would you like to choose? Using J1 or J2 based on the information that we have in front of us. I think either one is almost the same difficulty, so maybe I'll start with the J2. Okay. So here I'm going to calculate in the J2. And then you can look up the formula to getting those. So for J2, is the function from, you take the derivative of the g, your transformation, with respect to the original random variables. Okay, so here we have the g1, z and the v with respect to z. We also have the g1, z and the v with respect to v. For the second row, we have the g2, which is also the function. Okay, and then calculating the determinant of this 2 by 2 matrix. Here, I'm just copying down the formula, but using the variables in this context here. Yes?
What's the difference between J1 and J2 again?
So, back to last week. So if you choose to use the J1, then when you're in the end of the transformation, you just need to multiply by the absolute value of the J1. If you choose to use the J2, just don't forget there's an inverse. That's the only difference. And the mathematical intuition here is that the J1 is that you're taking the inverse function with respect to the new one. And the J2 is the transformation with respect to the original one. So that's why kind of explaining why you need an additional inverse. Because you are using the new with respect to the old one, or using the old with respect to the new one. So you need an extra inverse.
So would you just do whichever one is easier?
Yes. Yeah. Like on Tuesday, we are the other one is clearly easier than the other one, so we use J1 on Tuesday. Yeah. But today, based on these transformation, it's not too obvious, so either one works. Yeah, but they all provide you the same answer. So even if you want, during the exam, you can try both methods to see if you are doing correctly or not. So if two methods give you the same result, that means you are doing it correctly. Also kind of like a self-validation procedure. Yeah. But here it doesn't really matter because they are all quite difficult, so I'm using J2 for now. Any other question or comments? Okay, so now using J2, the dt, dz, so now I'm just replacing the G1 and G2 by the actual name of that random variables. Okay, so now let's take a look at the formula that we have for t. So earlier we noticed, or by construction, this is the formula for t. And our first input is that we need the g1 with respect to z. So what is the derivative of g1 with respect to z here? Well, we know g1 is that. Our 1 entry is the derivative of g1 with respect to z. So what is our,
1 over square root of v divided by k.
yes, exactly. 1 over v divided by k. Okay. For the second entry, we need g1 divided by, with respect to v. Okay, so this is slightly difficult, but let's work on that. Okay, so here we have a fraction where the denominator is another fraction. So let's rewrite this a little bit differently. So we have the z as itself, and then divided by another fraction. So for the denominator there can be transferred into the numerator. So we will have a square root of k. Okay. And then in the denominator, we have a square root of v. So when we write the fraction, we'll write for the denominator, we'll add an inverse. But we'll also have additional square root. So we'll write negative 1 over 2. So multiply by v, raised to the power of negative 1 over 2. So this is just another way by re-expressing that fraction form in a product form by giving the appropriate power for the term. Okay. Any question up to this point or for this transformation? And the reason is that once we write everything in terms of a product, it will be easier to take in the derivatives with respect to v. Okay, so now once we have all the products, then with respect to v for g1, with respect to v, we will have the following. So we'll have so the power is negative 1 over 2, and take derivative, you will have the negative 1 over 2 in the front, and then v for the power minus 1, so you will have negative 3 over 2, multiplied by z, multiplied by square root of k. Any question regarding these two entries? So again, based on all the information that we have here, g1, taking these two expressions, and then the inverse that we can obtain by rearranging terms to obtain the inverse function. So using the method of transformation, you need to calculate the Jacobian. You choose to use the J2, and you can copy down the formula for J2. The first two entries are the derivative of the J1 with respect to the Z and the V, and then we just use the formula for G1, taking a derivative of that. For the first one with respect to Z, just removing the numerator. For the other one, slightly difficult because it's a fraction of fractions. So usually you can write it as the product terms, and then from there, it will be easier to calculate the derivative. And you will have the following form. Any question up to this point? Okay, once we have handled the G1, let's handle the G2. So the G2 is just equal to V, or S equal to V. So now, when we take derivative of the G2 with respect to Z and the V, so what is the G2 with respect to Z here?
0.
There's 0, right? There's nothing in front of the coefficient. What about with respect to v. S with respect to v. Just go to 1, right? Okay. And then the determinant of this matrix. And the determinant of a 2 by 2 matrix is the diagonal, the product of the diagonal minus the off diagonal. So you can see that regardless of what that term looks like on this one, once you multiply by 0, it will remove from the picture. So you only have one terms left. 1 over v divided by k square root minus a 0. So you have the a multiplied by d minus b multiplied by c, where you have the 0 involving, so regardless of that formulation, I just remove it. And let me also write this by taking the inverse, so you have the k over v squared. Okay, but is this Jacobian complete or not? Is there some concern up to this point? So one thing you notice that the Jacobian, after you calculate, is still involving the v, the original random variable. But our goal here is to express the formula in terms of the new variables, right? So you don't want any old random variable showing up. So again, replace the v by the new random variable. And luckily, we construct the v equal to s or the s equal to v, so we can just simply removing the v by rewriting the v in terms of s. Okay, so again, just as a reminder, our goal is to find a joint distribution for the new random variable. For our Jacobian here, our old random variable should keep showing up. So we're replacing the old by the new one, so that in the end there will be no old random variables showing up, only the new random variables. Okay, so I finished the Jacobian. What will be the next step here from the formula? Yeah.
Do you define the joint distribution of C and
Yes, and then doing the transformation after that. Yeah. So exactly. Thanks. That will be what we'll be doing now. Okay. So first of all, let's find the joint for z and v. And here, there's one more component I need to mention, is that the z and the v are independent. Okay. So here, let's assume that they're independent. Okay. So based on the independent assumption, the joint distribution for the z and v is just equal to the marginal of the z multiplied by the marginal of the v. Again, as a reminder, z following a standard normal, v following a chi-square or gamma distribution, k over 2 and 2. Okay. Since they are independent, the joint is equal to the marginal, and we also know the distribution for each of the z and the v. So now let's input the density function here. So for z is the standard normal, so we have the 1 over 2 pi, the exponential negative 1/2 z squared divided by 1. So you can just write that. That is the density function for the standard normal. Okay, so that's the f of z, the standard normal density function. And now we also know that from the momentary function on Tuesday, we know that the v also following a gamma distribution. So we can use the density function for the gamma distribution. We will have the v raised to the power of alpha minus 1. Alpha here is the k/2 minus 1. And then multiply by the exponential of the negative v divided by beta. So beta here is 2. So we have that. And then beta raised to the power of alpha, we will have 2 raised to the power of k/2 multiplied by the gamma function of alpha. And then alpha is k/2. Okay, so this is the marginal for the v or the gamma density function. All you need to do is just replacing your new alpha and beta. Alpha and beta is from here, which is the momentary function we derived on Tuesday. Any question up to this point? Okay. Once we have the joint for the z and the v, what is the next step we need to do here? Yeah.
How put one of the variables, either z or v, in the form of the other variable, so that we can
Sorry?
put z or v in the form of v or z, respectively, so that.
The new random variable.
Oh no.
Sorry, what?
I didn't think these random variables. I was just thinking. Oh, yeah, there.
It's by replacing the new into the picture.
Yeah.
Yeah, exactly. Yeah. So again, these are expressed in terms of the old random variable z and the v. But again, we are interested in the density function for the new random variables. So the next step we need to do here is that whenever you see a z or a v, replacing by the inverse function that you defined earlier. So the inverse function are these two. Whenever you see a z, replaced by your inverse function. Whenever you see a v, also replace by the inverse function. So in the end, you will have your function only involving the new random variables. Okay. So this is the joint for z and the v, but what we want is the joint of the t and the s. So we want the t and the s. Okay, so for the first part, there's only a z showing up on the square term. So, and also the z is just equal to this one from the inverse function. So let's replace the z by its inverse, from the inverse function. The 1 over square root of 2 pi exponential negative 1 over 2, and then we have the z. And then from the inverse function, we find out that z is equal to t multiply by the square root of s divided by k, taking a square. Okay, so there's no more z showing up in the picture. Okay. Now let's bring the s into the picture by removing from v. Okay. Earlier we showed that the v is equal to s because we define s is equal to v. So whenever we see a v, just replace by the new random variables. So here is the new random variable raised to the power of k over 2 minus a 1 negative of s over 2 divided by 2 of s over 2, k over 2. Okay, so now you can see that there will be no more original random variables showing up. On the right hand side, only your new variables, the t and the s, showing up on the right hand side. So we have now removing all the old random variables from the picture. Okay. Does this complete the transformation or not? Or do we need anything else? In the Jacobian, right? Yeah. Okay. Because we also need using the J2, so what formula should we use here? Should we use the one with inverse or without the inverse? With the with the inverse? Yeah. Okay. So we need to use the J2 and then with the inverse. Okay. So J2 earlier we calculated is the k over s and then square root of it. And always don't forget there's another absolute value, but square root is already a positive number. So the square absolute value of that is just itself. But don't forget the inverse. So here you have the s. Maybe let me just write the k over s square root, and let me write the inverse explicitly. But inverse is just s divided by k. Okay, any question up to this point? So does this complete the transformation? It does, right? So right now we have the things expressed in terms of s and t. We also included the Jacobian. Everything is now involving t and s. So that means this is a joint density function in terms of the new random variable t and the s. Okay, so that completes the transformation. But there's one extra step that we want in this example, is that we want to find the marginal of the t. So we want to remove the s from the picture as well. So our first step is that after the transformation, we remove the old random variable from the picture. There's no more z and the v showing up, only the v and the s. But we need one extra step in this example, also by removing the s away from the picture. But let me pause here to see if there's any question after the transformation. So the whole procedure again, this is a third example using the same procedure. And I'm going to mainly test you on how to implement the whole step, the procedure here. Any question up to this point?
Will the one on the test be shorter or about this long?
I can't give you more information, but it's just the procedure. So maybe I can just do a quick recap, or maybe using the formula on last Thursday. Where is it? Yeah. So maybe I can give a quick recap on the whole procedure. And the only difference is that you need to find out what is your x, what is your g, and what is your h. Yeah. But the whole procedure stays the same. Yeah. Maybe I will not test you on too difficult transformation. But the same procedure stays the same. Yeah. So likely I'm going to give you some random variable x1 and x2 that follow some known distribution, so that you can find on your cheat sheet. I'm also going to provide you some transformation in terms of the g's. All you need to do is that first find the inverse function, like what we did in the past 2 weeks, and then decided whether you want to use J1 or J2, And based on whether your inverse or your g's are relatively easy, or whichever is easy, you can use either J1 or J2. After calculating that, setting up the joint distributions for the new random variables, whenever you see an old random variables replaced by the inverse function or replaced by the new variables, and don't forget the absolute value for Jacobi. If you use J1, then it's just the absolute of J1. If you use J2, don't forget the inverse of the J2. Once you bring everything into the picture, that will be your final answer. Okay? And the lectures on last Thursday, this Tuesday, and also today, these are all just exercise for you to using the same procedure. And then you can see that using the same methods, we can obtain some more new results. Okay, so by implementing the methods or the procedure, you arrive at this density function. And that concludes the method of transformation. And for the rest of, also from now, if you're not interested, then you can completely just ignore me. But now I'm just going to, doing this by, I want to introduce you the t distribution, which is something that you use very often, you just don't recognize it. Okay, so again, the next steps are not, if you're not interested, feel free to ignore me. But I'm just going to perform the marginalization. Okay, so now we have the joint density function of that. But now let me perform some more manipulation like we did on Tuesday. And then with some manipulation, that will give you some more new insight by looking at this lengthy expression. Okay, so first of all, I'm going to do by dragging whatever is a constant or not related to the random variable all the way to the front. Because in the later, I'm going to take a marginalization, which is the integral. So I want to make sure whatever is not involving the random variable s, I want to move it in the front. So that will clear my, my calculation. So anything not involving s, so now let me put it in the front. So here we have a square root of 2 pi. Okay, and then another thing is that here I got it as inverse. I want to kind of emphasize there's inverse, but essentially the square root of k is in the denominator, right? So I also want to bring that square root of k in here. So that is a square root of 2 pi k. So the 2 pi is coming from here, the square root in the denominator. After you take the inverse, the square root of k is also in the denominator. I want to bring it in the front, okay? But that's the k coming from the Jacobi. Okay. So this is a whole fraction here. Okay. Let's see. We also have a gamma function of k over 2. So let me bring that in the fraction. And also the 2 raised to the power of k over 2. Okay, so these are all the constant. Okay, next I'm going to group the remaining term. They all seem to involving s, so I want to grouping them in a more grouping them nicely to perform my integration later. Okay, so here let me work on the s here. So we have 2 copies of x showing up besides the exponential term. Okay, but there are 1 copy of x showing up here with the power k over 2 minus 1. we have another s showing up, which is in terms of the square root of s. Okay, so that means we have the s of k over 2 minus a 1, and then plus a 1/2. The 1/2 is due to, so let me rewrite, replacing this part, this Jacobian here. After you take the inverse, you have the square root of s over square root of k. So this k here goes to the denominator because that is in the denominator. And then the s is just s raised to the power of 1/2 and then square root of k. Okay? So the s raised to the power of 1/2 being carried over to here. So this is the s raised to the power of alpha minus 1, but k over 2 minus 1. There's another copy of s raised to the power of 1/2, so adding the 1/2 here. Any question up to this point handling the s? Okay. I'm also going to slightly clean up the power where there are 3 terms. So I'm going to clean up with the k over 2 plus 1 over 2 is just the k over k plus 1 over 2. Minus a 1. Okay? Instead of 3 terms, I just group them into 2 terms. So k plus 1 over 2 minus a 1 as the power for s. Okay. So the only thing that we have not yet covered is the 2 exponential term. Okay? Okay, for the exponential term, we have, and for that one, again, I'm going to using the e raised to the power of a multiplied by e raised to the power of b is equal to e raised to the power of a plus b. Okay, this is the formula, or the formula we're going to use. We're going to use that to handling the 2 exponential term. Okay. So here it seems like, let me handle the square term first. We will have the exponential negative 1/2, and then the square of that are just okay, so we have the t square and then multiply by s over k by removing the square root. Okay, multiplying by the exponential negative 1/2 and then the s. Okay, so now we have the e raised to the power of a and then e raised to the power of b. When they take the product, it's the e of the a plus b. So we need to sum the 2 powers together. Any question up to this point? Okay, so now let me just copy again the constant term. Okay, so now e of the a multiplied by e raised to the power of b is equal to e of a plus b. Sum them together, you will have the exponential negative 1 over 2 t squared over k plus 1 as a fraction multiplied by s. So I'm just grouping the constant in front of the s. You have the copy of p squared over k, and then a 1 here. So we have the sum of the t squared over k, and then plus 1 shared by the s in both terms. Okay, after this, we are ready to take the integral with respect to s. Okay, so now I'm going to take the derivative of this joint with respect to s. So I want to remove the s and then only keeping the t. And then the resulting density function has some statistical meaning, which I will introduce later. But now let's obtain the final formulation. Okay. So we need to take the integral with respect to s. So the constant term that we put it in the front is not going to be affected, so we can bring that in the front. And the integral is only going to affecting on whatever involving the s. So here we have the k plus 1 over 2 minus a 1 multiplied by the exponential of the negative 1/2 s multiplied by t squared over k plus 1 ds. Okay, by looking at this formulation, does the terms inside the integral reminds you of anything here? Does that look very familiar in some, or resembling to something that on the cheat sheet?
Gamma distribution.
More specifically, what of the gamma distribution?
The kernel.
The kernel function, right? So again, if you look up your lecture notes from probably week 3 or 4, this is the kernel function of the gamma. And then we give a definition for the kernel using the kernel function, right? Back then. So look up your formula for week 3 or week 4. Look up the kernel function. So now your alpha is the k plus 1 over 2. Your beta is just this one, bring it into the fraction, right? So using your formula, or look up your formula to recognizing what is the alpha and beta here. So let me just write down. The alpha is the k plus 1 over 2. The beta is 2 times the t squared over k plus 1, but taking the inverse, because the kernel function has the x over beta, okay? So in our case, it's s over the beta, so you need to put the beta in the fraction form. So that's why you need to have the 2, but also with the inverse, because you need to push the beta to the fraction, okay? So put the beta into the denominator of that 1 over 2. Okay, so once you have that, you're recognizing this is a kernel function of a gamma distribution. You're recognizing what is your alpha and beta. Using the definition back then, you will have the integral. You can solve the integral without just using the formula, without solving the integral. Okay. Maybe just let me provide, if you don't know what I'm talking about, so look up your lecture notes on the kernel function or the gamma distribution. Back then, we introduced the following. We have the integral from 0 to infinity, x of alpha minus 1, exponential of the negative x over beta. Back then, we called this the kernel function of the gamma density. This is equal to beta raised to the power of alpha, the gamma function of the alpha. Okay, so this is from week 4 or week 3. Look up the notes. And here we are using the identity again to calculating this. So on the right-hand side, we have a very complex integral to solve. But instead of directly working on that, you can see that you have two s showing out. Very likely you're going to use lots of mathematical tricks to solve that. But here we introduce a definition. Instead of solving that, you just need to recognize what is your alpha, what is your beta, writing everything in terms of the right-hand side. Okay? So all we need to do is to write everything in terms of the right-hand side, replacing the alpha and beta with our context here. That means you will have the 1 over 2 pi k square root okay, and then beta is the power of alpha, so beta is 2 times t squared over k plus 1 raised to the power of alpha, so it's a negative k plus 1 over 2 multiplied by the gamma function of alpha. Alpha is k plus 1 over 2. Okay, and then that's it. You can see that this expression only involving t, no more s showing up. We have to remove it by taking the integral by removing the s away from the picture. So this is the marginal density function for the t. Okay, and if you want, you can also group things a little bit differently. So let's see. You need some more algebraic things, but let me just provide you the final answer. So let me put the k plus 1 over 2 on the numerator. You have the square root of the pi k multiplied by the gamma function k over 2 1 plus t squared over k okay, and that is the probability density function for the t distribution. This is the PDF of the t distribution. Before I comment on this formulation or on this thing, any question regarding the mathematical part? Okay,
Can you scroll up a little bit?
scroll up.
Yeah.
Okay, that's the kernel function. You need to recognize your alpha beta, replacing to that, and a slight manipulation on this. So now if you Google what is the t distribution, this is the thing showing up in the Wikipedia. Okay. And any question before I talk about, or some comment, maybe some history or the usage of this one? Yes.
So, what is the significance?
I will talk about that later.
Oh.
Yeah, but now I'm just asking if there's any question regarding the manipulation first.
Oh.
Yes, yes.
Can you remember how you got the term for E into the sentence? What was that?
Anything up to here?
Like that whole like E.
Here? This the term.
Yeah, how did you get to like E to the negative 1/2?
Okay. So I'm using the formula of E of A multiplied by E of B equal to, right, that's the one I'm using. Here I have the E with power of A, right, E with power of B. Using that formula is the E of the A plus B. with that.
And how did you get the first part, that negative 1/2 t-squared decimal?
You mean how do we get this one?
That first chunk.
This chunk here. It's coming from the here. This one. Back then, the density of the standard normal is a z. Right? I replaced the z by the transformation of this. That's squared, so you have the t squared, and then s divided by k.
Oh,
The square takes care of the square root. Right? The t of the s divided by k. Let me. Okay, so I think if I. So here, the t squared is that the t raised to the power squared. S over k is the square of the square root of the s over k. You will have that. Does that answer your question? Yeah. Any other question before I comment on some of the history or on this one? So the guy who come up with this expression, back then he's working on a what they call brewer alcohol company, and then the company was asking this person to measure some recipe of making beers. But back then there's no way to analyzing the quality of the beers before and after treatment. So the guy decided to perform some manipulations, like what we did here, come up with a t distribution. The person is also writing papers to a very public, top tier journal. And the guy did not release his own name, but called himself the student. So when you're looking up, people always referring this as the student t distribution, because he did not want to reveal his name. He called himself the student. So very often this is called a student t distribution. And again, back then he's trying to analyzing the quality of the beer before and after treatment. So that providing us a powerful tool called the t-test. Okay, so in in most of the analysis, you are doing this t-test for comparing whether a treatment is really affecting or not. Okay. What you are doing is that you will collect some data point, let's call x before, or let's call x after a treatment. Let's say you have 1,000 or 100 patients, and then you're taking the average. You also have the x for the before the treatment, or the other group A or group B. You're interested in whether the treatment is going to be 0 or not. So if it is not 0, that means your drug or your treatment after is affecting. Otherwise, if it is strongly equal to 0 or very small, that means it's not very affecting. So you don't want to develop that drug anymore. Okay, or you don't want to make using the new recipe for the beer anymore. Okay, so in terms of the quantity, in terms of the population quantity, you will have the mu of after minus the mu before. And then in analysis, people usually make up hypotheses. So your hypothesis, which people usually denote as H of null, and you will write down that the H null is equal to 0. And based on your null hypothesis, that means your treatment after and before, there's no effects. Your drug is not useful. So you are testing under the regime when you assume your drug is not useful, and then based on the data that you collected, you want to see what is the probability of that. Okay? And then usually this one follow the student t distribution. Okay? And then what you're doing is that using the t distribution, so this is the t distribution under the null hypothesis when your drug has no treatment. You will be calculating the probability based on your data, based on your patient data, and then calculating the probability like what we did in the normal distribution. So if the probability of observing the differences that is very large and more than that value. If it is less than 0.05, which people call this the significant level, this is something that you need to define as a researcher. So if the value based on your data has a probability that is way smaller than your significant level, then you're saying that it is highly unlikely that the data that you collect, the data that you observe, is coming from this null distribution, where you assume the null has no effects. And then you will reject the null hypothesis. That means your treatment is unlike, your data collected is unlikely from a distribution where there's no effects. Because you started with you assuming that there's no effect. You use your data, calculate on probability, and if that probability is small, then you have statistical evidence to reject the null, where your null is saying that there's no effect, and you have statistical power to reject your null. That means your drug is having some effects on the treatment or on the X that you are measuring, and that is what this distribution is useful for. And then I'm very sure you guys are doing that, but just you don't recognize it. That is the density function that you are using to calculate this probability, which usually people call this the p-value. So the p-value that you're calculating from is from this density function up to the data point that you collected. Okay, so that is what I want to talk about this. But again, it's the procedure that up to the transformation that I will be covering on the final exam. Okay, that'll be all for me.